Okay, so this presentation is more theoretical, and I want to make to show that when you swim, so when a fish swims, you can interpret from the theoretical control theory point of view, you can see as doing Lie brackets, and it is what I want to explain you in this talk. So first I have to introduce what means Lie bracket and what is usually done when you present Lie brackets in control is to start with a Dubin's car. So a Dubin's car is like this. You have a car, the blue one, that has to park, and you cannot go directly in this direction. But if you move front and you turn and alternating like this, so it's some kind of Lie brackets, then you can go to this direction. You can go laterally. So it is a well-known result. A lot of work has been done, especially by Lomont, for instance. And I take the Dubin's car, classical mobile robot, I would say. So you can control U1 corresponding to the speed and U2 corresponding to the rotation, like this. And it is a driftless system. So what is a driftless system? I could rewrite the Dubin's car like this. So there is some linearity where you can say that there is two vector fields, f of x and g of x, both depending on the state. And U1 and U2 are the control because they appear linearly. And if suddenly I put U1 and U2 equal to 0, then the vehicle stops. So it is what we call a driftless state. But of course, when we have robots like when we want to swim, we have some drift. But here, in classical control theory, we take driftless system to introduce Lie brackets. So what is a Lie bracket between two vector field f and g is defined like this. Okay, so I define very quickly like this, so I can compute them. It is important to know. And for the Dubin's car, where I have f of x and g of x, if I compute the Lie bracket, it corresponds to the vector product. Okay. So it is a new direction which corresponds to the lateral direction. Okay, so if I consider a very general driftless system like this one, then if I take some periodic inputs, so U1 and U2 are two inputs. It's important for swimming to have two inputs, not one. One is not enough, as shown by the scallop theorem, which shows that you cannot swim with only 1 degree of freedom, with one control. Okay, so I need two. So if I take some periodic inputs, of course, when you swim, you have to do something periodical. So in the input space, I compute the integral, and the integral will make a cycle in the space U1 and U2, and it will describe an area. So I will illustrate now. And so this area is like this. So U1 and U2 are the integrals of the input U1 and U2. And it will perform a circle or a cycle. And this cycle has some area, I call it A. And this area will tell you how you will quantify how you will move laterally for the Dubin's car, or internal, how you will move along the Lie bracket. Okay. So if you apply a control corresponding to a cycle like this one, you will describe an area, and you will have a shift between the state at time t and after the period delta, which will correspond to this displacement will be along the Lie bracket and proportional to the area you made. So for the control, it's important to have an area as big as possible. And in practice, we take squares. like in the book of Laval, for instance. But it's also, you can take a disk. So we will take a disk for to have some differentiable inputs. Okay. So if I take a disk, the corresponding input would correspond to cosine sine, and I have to compute the gain here in front so that I move laterally for the Dubin's car at the speed I want. So in some sense, I can control the speed, how the car move laterally. Okay. The corresponding control is this one. I have my driftless system. U1 and U2 correspond to how I move for my Dubin's car. And if I apply the Lie brackets or the cosine sine along the circle to perform an area, then I will have a new input corresponding to A3. And I was able to introduce a new input A3, which allow me not only to move as I want along F and G, but also along the Lie brackets. Okay, so this input corresponding to A3, I can represent like this. And you can see that I have to go, if I want to move laterally, and I have to have some inputs that perform some area, so they have to be huge, and also the period should tend to infinity to have the feeling that the real car move laterally and smoothly. So of course, we have some kind of vortex distribution, which is a strange mathematical object, and I will not enter in this. Okay. So in practice, we cannot go very fast along the Lie bracket. And for swimming, we'll need to go fast. Okay. So I will now show the importance of the drift. For the Dubin's car, recall I have this, F and G. The Lie bracket can be computed as I have shown before. And if I apply the cyclic sequence, I introduce a new input A3, which looks quite strange to be able to add a new input like this. And in force simulation, I can show that I can move in all directions as I want. And when I show this kind of picture, you can have the feeling that it's just a representation where you can see the car here, which looks like doing 10 meters, in fact, is doing 1 centimeter. Okay, so it's just a graphical representation that can show that you can move laterally. Okay, now for swimming, I will consider not a fish, because it's difficult to get the equation, but a skate car. So a skate car is a specific object represented here when you have 5 wheels or 5 blades and you have to oscillate to be able to go forward. So you have 1 wheel or 1 blade in front, and here 4 like this. You can control the angle U1 of the first blade, and here the torque U2. And with this, I can get the state equation where x, y, theta correspond to the pose, v to the speed, and alpha, beta, the angle as represented here, beta and alpha. Okay, so if I just consider the velocity part, not the position, but just the velocity, the equation becomes simpler like this. And I observe that I have a drift system because I have F here, but here you can have G1 and G2 when you will be able to do Lie brackets between G1 and G2 and also F. Okay, so if I consider G1 and G2, and if I compute the Lie bracket, then I make appear a new direction like this. And this direction corresponds to the velocity of the vehicle. And it is important for swimming object that the vector field between G1 and G2 corresponds to the direction when you want to go. Okay. So it is the case here, even if I have a -1. And if I apply the controller I introduced for the Dubinscar, which is given by this formula, which makes some cycle, then you will have this controller where the new input is not U1 and U2, but A1 corresponds to the direction and A2 corresponds to the speed where you want to go. So with this object, you can have the feeling that you are able to control the speed and the direction. So let me take my system like this. G1, we recognize, so after the loop like this, I have this new system where A1 and A2 correspond to the direction and the speed. And I apply a classical control system, for example, a proportional control system, so that I am able to go to the speed I want and to the direction I want. Okay, so if I do this, I have my system. So I do not show you the simulation because I don't know how much time I have. I have no clock here. Sorry, I cannot see in my computer. But I can see my vehicle starting from 0 and oscillating like this. And if I oscillate for a long time like this, I am able to control the heading, still oscillating, and also the speed. For considering the inputs, they have this shape, or if like this, and you will converge to something which is not 0, because you have to make a proportion, but at the beginning, you had to put more efforts. And if I show the speed, I will converge to the wanted speed, will correspond here to 100 in my simulation. Okay, so now my last thing was to make a relation which what is a swimmer, what is an abstract swimmer, so what is a vehicle that swims, and try to define mathematically what it is. So in fact, to have a swimmer, I need a state equation like this. I need two inputs, U1 and U2. I also need, for my state variable, the speed, which corresponds here to my first state variable, V. So it is important to have V. I need to have V, which is almost driftless. And it is the case for fish, for instance. We can assume that we have some friction, of course, which slow down the fish, but it's almost driftless. Okay, so it means that the f1 of x is almost equal to 0, just some friction. And it is important also to define the abstract streamer, that the Lie bracket between G1 and G2 goes to the direction of an evolution for V only, and only for V. Okay. And it is a way I define an abstract streamer. Okay. So you can imagine like this. I have a fish, which is described by this type of state equation with two inputs. And G1, G2 correspond to this direction. I mean, to moving in some direction I want to go. Okay, so for the state car, I change to put the first variable at the beginning, okay, to correspond to my formalism. And you can see that in the model I gave, I had no friction at all, but in practice, you have a small friction here, but it is small. And if I compute the Lie bracket between G1 and G2, I move toward the first state variable, I mean toward V.